Hi, I'm Yassine, and this video is basically a devlog of the entire process it took me to build a custom freezer controller, about the challenges I faced, and the little twists. Now things can sometimes go out of scope in one way or another. Now, quick disclaimer, this video is not a guide by any means. None of what I'm doing particularly makes a lot of sense. I'm mainly doing this because I can and because I want to, and if your freezer stops working, you should probably get it checked by a professional. With that out of the way, how does a fridge work? Well, a fridge consists of a lot of parts, and we don't really care about everything. What we care about is the control aspects of it. It consists of a temperature sensor to measure the actual temperature of the fridge, and it consists of, let's call the compressor. The compressor is connected to a lot of other things that are very crucial to the cooling process. We don't care about those right here. We're just gonna consider the compressor. And it consists of a controller to regulate the process of all of this, to keep the compressor on only when it needs to be on and turn it off when it doesn't need to be on. Now, in some older fridges, these two parts are combined together and it's called a thermostat, but that's not what we're talking about here. In the newer fridges, it's a control board that takes care of reading the temperature and controlling that. And that's what I'm going to be making here because the one I have stopped working. So how do I know that that's what stopped working? Well, I checked everything individually. I started by checking the temperature sensor that I have by measuring it with a multimeter, and it seems to be reading 11 kilo ohms, which sounds about right for a 10K kilo ohm NTC. And I also tried to directly connect the compressor by hooking it up directly, and it actually worked. And the cooler started cooling. One might ask, if I can just do this and the freezer is actually cooling, why can't we just leave it this way? Well, as I mentioned previously, it needs to be regulated. You can't just run it like that. One of the things is that if you let the compressor on for too long, it'll end up overheating. The first thing I did was build a proof of concept to make sure that I can actually, apply the idea. At the heart of our proof of concept is a microcontroller, and there are quite a few choices we can choose from. After all, what we're doing is kind of simple. After a bit of thought, I decided to choose the Arduino Pro Micro. It's small, has enough power. This choice might come back to haunt me later, but anyways, I quickly connected the circuit on a breadboard. I mean, it's kind of simple. I just needed to read the temperature sensor, and I needed to control the compressor by turning it on or off. Now, in the original control board that stopped working, they were using what's called a triac to control the compressor. Here, I'm just using a relay because it's easier to set up. No, nothing particular about that. And I also added a small screen just so I can visualize what's going on without having to have my computer connected to it all the time. And it seemed to work. The freezer was getting colder and it seemed to be maintaining the temperature it was supposed to be at. Now this was meant to be a temporary solution, but I might have left it there for about 5 months. It doesn't exactly look like the way it looks like right now. It's a little bit better, but anyways, it was still meant to be a temporary solution that I completely forgot about. Once I was done with the proof of concept and I had the basic idea and I was sure that everything worked, I decided to build the permanent solution. But I was like, I'm making something, why don't I add a few features here and there? And the scope started getting a little bit out of hand. I decided I wanted to have an interactive menu in the controller to allow me to, change the temperature, change all the parameters that I have and all of that. And to do that, I need a good screen and a knob. And I also decided maybe I want to measure the temperature of the compressor itself. So that's one extra temperature sensor. After adding all of these parameters, I wanted to be able to know if the parameters I chose were actually good or not. I needed to be able to look at the data on a longer scope of time, from far away. So I also added an SD card, so I can log the data, the temperature, the current settings, and all of that. But here's another thing. If I wanted an SD card, I needed to be able to relate the data to real world time. So I added an RTC clock as well. You see what I mean by the scope starts getting out of hand and I started adding all these unnecessary features? And we can pause for a moment and, think, does any of this matter? No, it really doesn't. But again, I'm doing this because I want to. So yeah, we're just gonna move on. To turn this into a permanent solution, I decided to make a printed circuit board PCB. The process of doing that starts by designing it. I used a software called KiCad, and I started by drawing all the schematic, connecting everything together, and then choosing the actual physical footprints for all the pieces. And afterwards, I moved on to the routing, which is essentially like a puzzle, connecting all the pieces that need to be connected together without crossing the other stuff. Now, for this design, it's pretty simple. It doesn't really matter too much how something is connected to the other as long as they're connected. But for more complicated designs and coupling things, that really matters. But we're ignoring that right now. Once that was done, I could have sent this design to a manufacturer in China or whatever, and there are quite a few good ones. However, due to where I live and how much money that would cost and how much time it would take to get to me, I decided I'd just make the PCB on my own. Now, it wouldn't be as good of a quality as if I actually ordered it from a manufacturer, but it'll be good enough for what we're doing here. The process starts by printing the design mirrored on a glossy paper on a laser printer. And yes, it has to be a glossy paper and it has to be a laser printer for this to work. Afterwards, we take a bare copper clad board, which is essentially a piece of plastic or fiberglass with a thin layer of copper on top of it, and we need to make sure it's clean. So I'm using a piece of steel wool to, scratch it up and all of that. What we want to do is take the piece that we just printed and transfer all of the ink or the toner from the paper to the board itself. We can do that using heat, and for that I'm just using a regular iron. Now, this process is a little bit finicky and it might not work properly from the first time. I actually had to do this twice to get it to work. But once it's done and we peel off the paper after letting it cool for a while, we can see that our design has been transferred from the paper to the board. Afterwards, I took the board and dropped it in some acid. Basically what we're doing right here is called etching. We want to remove all the copper in the places that are not covered while only leaving the copper that is covered by the ink that we just transferred. Now, there are multiple choices or types of chemicals you can use for this. The one I had right here is called ferric chloride. The issue though is it's kind of old and it's kind of saturated with copper and it needs a little bit of help to work. I could have done that manually by basically agitating the container for like 20 minutes or so, or I could waste half a day and build a machine just to do this thing for me. One of these choices makes sense, the other doesn't. But we both know which one I decided to do. Yeah. Anyways, once that was done, I left the container there for about 20 minutes or so, and after taking the board out, we can see that all the copper that wasn't covered with the toner or the ink has dissolved, which is exactly what we want. And after cleaning that ink off, I inspected the board under a microscope just to make sure that everything was okay, there were no cuts or connected pieces where they're not supposed to be, and everything was fine. The next thing that needed to be done was drilling all the holes, and there's a lot of them, and a drill press would have really helped here, but I don't have one, so I just used the hand press and went through them one by one. That definitely took a while. These are the holes where the components are going to be placed afterwards. There's also the silk screen that we gotta add. Basically, it's the layer on top that has all the labels and the writing. This is kind of optional, but it makes it easier to identify the different parts, and it just makes the board look cooler, which basically involves the same exact process we did earlier. We print it on a paper, we stick it to it, and we use heat to transfer it. After cleaning all of the edges of the board using some sandpaper, it was time to put all the pieces together. It was time to solder the components. So I took all of the components, placed them in their place, soldered them with a soldering iron. This basically holds them in place while also making a connection between them, between the copper traces. And with that, the printed circuit board was complete. The first thing I did was to connect it to a computer just to make sure that it actually turns on and there was no magic smoke or anything. and everything went well. This board is meant to replace the original board in the freezer. And I need it to be contained and also look good. So I designed an enclosure for the project using a 3D CAD software, and then I 3D printed it on my 3D printer. The red pieces right here are printed out of ABS, and the white piece is printed out of PLA. Now, normally you wouldn't want to use PLA for something that might be near a heat source or, might be left in the sun, but it's kind of covered and it's also white, so I figured it'll probably be fine. I also incorporated some heat inserts into the design that makes it easy to screw and unscrew the pieces together. I wanted to be able to take it apart if needed. I did not want this to be like glued shut together, basically. As with everything else in this project, things don't necessarily, work from the first time, and I managed to crack a screen in the process because the 3D printed part was a little bit too tight, and I had to buy another one and redesign it. So yeah, I'm kind of skipping a lot of issues and things that happen along the way. So if that ever happens to you, don't be discouraged. This kind of thing just happens. Once everything was put together, the next step was the programming. I gotta teach this controller to do what it's supposed to do. Now, remember how earlier I said that choice might come back to haunt me, the microcontroller that I chose? Well, it very much did. Now, the Arduino Pro Micro is very much enough to do the basic things that we need to do, or the most important part, which is controlling the temperature. But we want to do a little bit more than that. We want to have the interactive screen, we want to write the data to the SD card, we want to be able to read the RTC clock, and all of that. And that was an issue. I started hitting the flash storage limit because it only has like 32 kilobytes of space. And it was a constant game of adding things, removing other things, trying to optimize other parts. And there's a lot I want to talk about, but I can't fit it right here. So I wrote a blog post about how I had to manually write the data into the SD card without a file system. If anybody's interested, the link is going to be down in the description. But yeah, that was a hell of a process. I added a lot of different screens. I added an interactive menu, and I needed to make sure that things actually work without having it connected into the fridge. So I was dipping the temperature sensor in ice to simulate something very cold, and I also used my blowtorch to, simulate the compressor overheating or something being very hot or whatever. I added a little bit of safety features here and there. Yeah, overheating works. In general, that was one of the most things that took a lot of time. I was this close to actually, scrapping this PCB and creating another one using a different microcontroller. I got as far as designing another PCB, but I never really built it, and then I just, decided to explore more aggressive optimization techniques. If anyone's interested in more details about this part, I can perhaps even make a whole other video just about this, where I can, write more blog posts or whatever. So, if you have any ideas, leave them in the comments. After the programming was done, I put everything together, and it was time to remove the temporary solution that I left there for about 5 months collecting dust. I mean, it worked after all. That's the core of the idea. I needed to fix the freezer. But now it was time for the permanent solution that looked good. So I made sure to connect things quite tightly. This was meant to be permanent, so I routed the cables and all of that. And overall, the process wasn't hard. There were a few times where I had to take it apart to reprogram the microcontroller because of small mistakes I did. But in general, the process went fine and the freezer was working. I did face a few problems along the way. The first of them was the RTC clock that I added. Sadly, the chip that I chose is very unreliable. It might be due to it being a clone, but it was the only one that I had. It was constantly resetting, going out of sync and all of that. So sadly, I couldn't really depend on it. I was still logging the data, but I couldn't really link it to world time. I tried multiple things to fix this, but at the end of it, I just gave up. It was just not worth it anymore, even though this whole project is kind of not worth it, but that's a separate thing. The second problem that I faced was with the temperature sensor and the analog readings. Now normally during testing, the board was always powered from the USB, which gives about 4.8 volts or so. But the final product was actually using a power supply right out of a 5 volt wall brick. and that was giving a little bit over 5 volts, about 5.35, and that was enough to make quite a substantial difference in the analog readings, which is how we're reading the temperature sensor. So I just solved this by adding a diode in line with the power supply. This diode had about 0.6 volts of voltage drop, which was enough to, make the voltage from the power supply down to right about 5 volts. So yeah, that was it. That was the process of building the freezer controller. There are a lot of steps and issues and things that I faced that I skipped over because of time and because the video would just become too long and boring. If you want to learn more about it, again, I can make a separate video specific to the details, or you can ask questions and I can answer them. And that includes all the different parts, from the design of the enclosure to designing of the PCB to the Python script that I had to write to visualize the data that I'm saving to the SD card and all of those details. And that's pretty much it. I hope that you guys enjoyed watching the video, perhaps learned a few things, and see you next time. Bye.